So, let us start with the example which we did in the last class for solving one integer programming problem, linear programming problem. So, just to recap, your problem was this: using the slack variables, we made it in the standard format. We made the simplex table. There we found that zj minus cj is less than 0. So, most negative, that is x1, x2 was the entering vector, and after calculating the ratio, x3 was the outgoing vector. So, in the next table, whatever we have formed x2 and x4, then we recalculated it, we calculated the value of zj minus cj. What we are finding out is zj minus cj is greater than equals 0 for all j, but the feasibility condition is not satisfied, since value of one of the basic variable, that is x2, this is equals to 4 by 3, that is non-integer. So, now I have to use the Gomorian method to avoid this non-integer value. So, what we are finding here is that fractional part of xbi, your fractional part of xbi, that is xbi means here it is x2 and x4. Fractional part of xbi is which one? 4 by 3. This value of x by 2 is 4 by 3 and it is 22 by 3. So, from here the fractional part is equals to 1 by 3. The fractional part is 1 by 3. Now, you have formulated this equation, fb minus this one should be less than 0 to make it integer type. After that, we introduce the Gomorian slack variable. So, I am writing that equation itself, f of bk minus summation over L equals m plus 1 to n f of kl xl, which is this is xl less than equals 0, where f bk is the fractional part of the x bk. So, I have to find out what are the values over here. What is f10? Your f10 is the fractional part of b. Fractional part of b means xbi. Fractional part of xbi already we have shown as 1/3. So, f of 10 is 1/3. Once I am doing this one, then on this, in both cases it is 1/3. So, any one I can take, I am considering the first row. Then how many more fractional parts are there? Here you have 2 more fractional parts corresponding to this. This we have not considered because this is negative. So, your f11, this will be equals to half, and f13, this is 1 1 1 2 1 3, f13 this is equals 1 by 6. So, what happens here? fbk, that is f10 minus this is f11, x1 corresponding value will be x1 plus f12 x2, sorry, this is 3. So, it will be f13 x3, this is less than equals 0. So, if you substitute the value here, from here you will get 1/3 minus half x1 plus 1 by 6 x3, this is less than equals 0. So, if you note this one, that please see this thing. At first I am finding out the fractional part of this, fractional part of this is 1/3, of this one is 1/3, otherwise maximum one I will take. Now, I have to use this inequality whatever we have shown earlier. On this inequality, now f10 will be equals to b, that is the fractional part. If I consider this row, because both are 1/3, then I have to take the fractional parts on other columns. Here it is if it is f10, this will be f11, this will be f13. So, f11 half, f13 6. So, this equation inequality can be written as this. From here we are getting this less than equals 0. Now, this constraint I will make it equality constraint by applying the Gomorian slack variable, and I will reconstruct the table from here. I will reconstruct the table from here, that is, I will write down minus x 1 by 2 minus x 3 by 6 plus S 1, this is equals minus 1/3, where S 1 is the Gomorian slack variable, and this particular constraint now will go to the next one. This constraint will now go to the next one. Next one means what? Will go into this one. That means already you are having only two variables in the basis x 2 and x 4. Now, one more constraint, basic variable S 1 will be added over here, and this row also will be added. So, in the next iteration, next simplex table will contain three basic variables, x 2, x 4 the earlier ones, and new one is S 1. So, we are constructing now the new table which will contain x 2, x 4 and S 1. So, this will be y 2, y 4 and S 1. Values are 1, 3, 0, 0, and please note that for slack variable also the value will be, the coefficient will be 0. So, that here you will obtain 3, 0 and 0. So, once we are doing it, we are writing this one 4 by 3, half, 1, 1 by 6, 0 and 0. Please note that these two rows will remain as it is, there will be no change. These two rows will remain as it is, and one more row will be added with the coefficients of this one. So, next row will be 22 by 3, 4, 0, minus 1/3, 1 and 0. And the third one is value of b here is minus 1/3. So, therefore, it will be minus 1/3, minus half, 0, minus 1 by 6, 0 and 1. So, now like this way, whenever you are having one table where Zj minus Cj is greater than equals 0, but the solution is infeasible, since one of the value of the one of the decision variable or basic variable is fractional. So, by this way you are calculating what is the fractional part, maximum fractional part, and then you are this inequality you are calculating like this way, and you are formulating the table. So, now your Zj minus Cj value will be equals to half, 0, half, 0 and 0. Here if you find your Zj minus Cj, this is greater than equals 0, but the solution is infeasible, since S 1 equals minus 1/3. As we mentioned earlier, whenever you will introduce the new constraint and you will add the Gomorian slack variable, always the value of the Gomorian slack variable will be the negative one. Now, if it is negative, we know how to find the how to find out or eliminate the negative value in the basis using dual simplex method. Using dual simplex method, always we can do this one. So, in this case, your what happens here, maximum of here negative is coming on this thing. So, maximum of this divided by this, because negative is here, negative is here. So, maximum of half divided by minus half and half divided by minus 1 by 6. If you do it, you will get maximum of minus 1, minus 3, and this is equals minus 1. So, this is equals to minus 1. So, therefore, without going in details, because this thing we have discussed earlier, this will be your departing vector and this will be your entering vector. That means, this will be the your pivot element. So, please note that on this, since your basic variable value is negative, so we are using dual simplex method. We are using dual simplex method to eliminate this one, and from there we are finding what is the outgoing or departing vector. Your departing vector will be S1 and your entering vector will be Y1. So, therefore, in the next one S1 will be replaced by X1. So, let us formulate the next table. In the next table now, you are having X2, X4 and X1, because X4 has been replaced by X1. You are having Y2, Y4 and Y1. Here it will come 1, 3, no change, 0, 0, 0. So, CV's values will be 3, 0, corresponding to Y1 it is 1. So, now it is becoming 1, 0, 1, 0, 0, 1. Then there will be 14 by 3, 0, 0, minus 5 by 3, 1 and 8. It will come as 2/3, 1, 0, 1/3, 0 and minus 2. Calculate the Zj minus Cj, it will be 0, 0, 1/3, 0 and 1. So, again if you find here, it is Zj minus Cj is always again greater than equals 0. But if you find here x1 is 2/3, x4 is 14 by 3. So, these are non-integer values. So, therefore, I have to eliminate 1 from this. The fractional part for both case x1 and x4 is 2/3. The fractional part of x1 and x4 is 2/3. So, therefore, we can use any one of these two. I am using say x1, there is a tie, both are same. If I am using x1, then f10 will be 2/3. I am again repeating this, f10 will be 2/3. I would have taken this one also. So, f10 is 2/3 and on this row you have only one fractional part, that is 1/3. So, f11 will be equals to 1/3. Therefore, your inequality will be 2/3 minus 1/3 into 1/3 belongs to x3. So, it will be x3 which is less than equals 0, or this I can write down minus 1/3 x3 plus s2, this is equals to minus 2 by 3. So, in the next one what happens? Since there was a fractional part in both x1 and x4, therefore, what we have done, the fractional part is 2 by 3. So, I have to use a new constraint, Gomorian constraint, to remove the fractional part. Since there is a tie, I can use any one. I am using say x1. Then your f10 will be 2/3. There is only one fractional part, 1/3. So, you are getting this inequality. By adding the Gomorian slack variable S2, you are getting this constant, equality constant. Now, this will be added on the existing table, that is on this table it will be added over here. So, once this is added on the basis, now you will have x2, x4, x1 and S2, this will be added. So, once we are adding this in the next table, what you will obtain? X2, X4, X1 and S2. These are Y2, Y4, Y1 and Y2. Here the values are same 1, 3, 0, 0, 0. The slack variable you see we are removing from here, because slack variable is not necessary. So, it is 3 0 1 0 corresponding Cj values, and again what you will do? You will write down this entire table, along with that you will add this row together. So, it will become 1 0 1 0 0 0 14 by 3 0 0 minus 5 by 3 1 0. For x 1 it is 2 by 3 1 0 1 third 0 0, then minus 2 third 0 0 minus 2 third 0 0 minus 1 third 0 and 1. Calculate the Zj minus Cj value, you will obtain that this one. So, your Zj minus Cj is greater than equals 0 for all j, but the solution is infeasible since S2 equals minus 2 third. Therefore, you will use the dual simplex method since the value of a basic variable is negative. So, if you use dual simplex method, which I am not explaining, you will find that this will be the outgoing vector, and that means S2 will be the outgoing vector, and your y3, that is x3, will be the entering vector. So, that your pivot element is this one. So, in the next basis S2 will be replaced by y3. So, once I am doing this thing, therefore, what you will obtain in the next table is, you are having this one x2, x4, x1, and S2 is replaced by S3. So, this is y2, y4, y1, y3. Cj values are 1, 3, 0, 0, 0 and this is 3, 0, 1, 0. The values you will get as 1, 0, 1, 0, 0, 0, 4 by 3, 0, 0, 0, 0 minus 5. For x1 it is 0, 1, 0, 0, 0, 1. This is x3, it is 2, 0, 0, 1, 0 minus 3. And if you calculate the Zj minus Cj value, it will be 0, 0, 0, 0. This is 0, this is 0, this is 1. So, you will get 1. So, your Zj minus Cj greater than equals 0, and for the decision variables, your original problem was maximize z equals x1 plus 3x2. So, therefore, your two decision variables were there, and here what you are obtaining, that the value of the decision, both decision variables are integer. Therefore, this solution is optimum, and you can write down your optimum solution as like this. Your optimum solution is x1 star equals 0, x2 star equals 1, and z max, maximum value of z is equals to 3 into 1 plus 0 into 1. So, this is 3. So, I hope it is clear to you now that how we can solve one integer programming problem. Let us take quickly one more example, so that it becomes clear to us. I am not reading the entire thing. The owner of a garment shop makes two types of shirts, known as A shirt and B shirts. He makes a profit of rupees 1 and rupees 4 for shirts of A shirt, B shirt respectively. He has two tailors X and Y. Tailor X and Y devote at most 7 hours and 15 hours per day, which you are coming here. Both type of shirts are stitched by both tailors. Tailor X and Y spend 2 hours and 5 hours respectively in stitching the A shirt, and 4 hours and 4 hours for a B shirt. So, how many shirts of both sides should be stitched in order to maximize the daily profit? So, here x1 and x2, I am assuming number of A shirts will be produced is x1, number of B shirts will be produced is x2. since we are producing both the sorts, therefore, I have to maximize x1, profit per A type sort is rupees 1 and profit per B type sort is rupees 4. So, objective function will be z equals x1 plus 4 x2 and they can first one they can stitch 2 and 4. So, this will be 2 x1 plus 4 x2 less than equals 7 and 5 x1 plus 4 x2 is less than equals 15. These two are the constants, x1 x2 are greater than equals 0. So, once I am doing this one here, since I have to prepare the sorts both of x1 and x2 are sort type, therefore, they must be integers. So, once you are writing it in the standard form, you can write down in the maximum of z equals x1 plus 4 x2 subject to again use the slack variables, that is 2 x1 plus 4 x2 plus x3, this is equal 7, 5 x1 plus 4 x2 plus x4, this is equals to 15 and x1, x2, x3, x4 is greater than equals 0, where x1 and x2 has to be integers. So, here your x3 and x4 are the slack variables. So, after writing it in the standard form, now we will write the corresponding tables as usual. From here again in the basis only two variables will go, that is x3 and x4. These are the variables which will go in the basis. So, in the basis you have x3 and x4. So, this is y3 and y4 and here values of Cj are 1, 4, 0, 0. Obviously, here we are writing 0 into x3 plus 0 into x4, because in this case the corresponding coefficients of the slack variables are 0. So, 1, 4, 0, 0 are the coefficients of x1, x2, x3, x4. So, the CV values are zeros. So, you will get 7, 2, 4, 1, 0. I am not discussing because this already we have solved so many problems till now. 15, 5, 4, 0, 1. Your Zj minus Cj is minus 1, minus 4, 0, 0. So, most negative is minus 4. So, this will be the entering vector. Calculate the ratio, it will be 7 by 4, 15 by 4. So, from here it is minimum is this. So, therefore, since minimum is this, your x3 will go out. So, that in the second iteration your x3 will go out and x2 will enter into the basis. So, from here we are writing x2 which is replaced by x3. So, here it is y2 and y4. Your Cj values are 1, 4, 0 and 0. So, CV values will be x2 is 4, this is 4, 0. Obviously, here your pivot element was this, that means I will make this element as 1 and this element as 0. For that, I will perform the corresponding row operations. So, it will become 7 by 4, half, 1, 1 by 4 and 0. For this, it will be 8, 3, 0, minus 1 and 1. If you calculate Zj minus Cj, you will find that Zj minus Cj is 1, 0, 1, 0. So, therefore, here if you find your Zj minus Cj is greater than equals 0, but the solution is infeasible since x2 is equals to 7 by 4. Since x2 is the fractional part here. What is the fractional part? The fractional part here is 3 by 4 and which is occurring here. Since x2 is 7 by 4, therefore, the solution is infeasible because you have the non-integer solution. So, the fractional part I am calculating here for only, it has occurred for one case. So, fractional part of 7 by 4 is 3 by 4. Therefore, this will be your F10 as usual in the last time we have told. So, F10 is equals to 3 by 4. It has on this row you have two fractional parts. So, your F11 will be equals to half and F13 will be equals to 1 by 4. So, your Gomorian constraint will be 3 by 4 minus half x1 plus 1 by 4 x3, which is less than equals 0. Now, add the slack variable and we can write down half x1 minus 1 4 x3 plus s1, this is equals to minus 3 by 4. So, now add this constraint over here, that is on the next table you will have the 3 variables x2, x4 and x1 and add this thing. So, you will get x2, x4 and x1 s1. You have added the slack variable as s1 over here. So, once you are doing s1 over here, so once I am doing this one, it will be y2, y4 and s1. Cj values are 1, 4, 0, 0, corresponding to slack also it will be 0. So, y2 is 4 and x4 is 0, s1 is 0, 0, 0. So, now you will obtain, you will add one more constant corresponding to s1. These two rows will remain same like the other one. So, 7 by 4 half 1, 1 by 4 0 and 0. Next row will be 8, 3, 0, minus 1, 1 and 0. Next one will be half Zj minus Cj is this will be minus 3 by 4 minus half 0 minus 1 by 4 0 and 1. Zj minus Cj if you calculate 1 0 1 0 0. So, Zj minus Cj is greater than equals 0, but the solution is not feasible since s equals minus 1/3 minus 3 by 4. So, since this is negative, so therefore, we will use the dual simplex method to obtain the solution of this. You know, you will find out the minimum and you will obtain what is the departing vector, what is the entering vector. So, using dual simplex method, your departing vector will be this one and your entering vector will be this. So, in the next table, your S1 will be replaced by x1. So, in the next table, what you are obtaining is x2, x4 and x1. So, this is y2, y4 and y1. CV values are not changed. So, it will be 4 0 corresponding to y1, it is 1. So, since it is the entering variable and departing variable, your pivot element is this. I will make this one 1, this as 0. So, I will obtain 1 0 1 0 1 1. Then I will have 7 by 2 0 0 half 0 and 6. I will have 3 by 2 1 0 half 0 and minus 2. Zj minus Cj if you calculate 0 0 half 4 2. But Zj minus Cj is greater than equals 0 for all j. But the solution whatever you are obtaining here, that is non-integer solution. If you find here corresponding to x1 and x4, the fractional part is half for both cases. So, I can choose any one. If you remember in the earlier case we choose x1, now say I am choosing this x4. So, we choose x4 to eliminate. So, once I am choosing x4, so your f10 or f20, if you consider this is equals to half. Corresponding to this you have only one fractional part. So, f23 equals half here. So, your inequality becomes half minus half x3 less than equals 0, or introducing the slack variable minus half s3 plus s2, this is equals minus half, and this will go into this table. So, now in the next table what will happen, you are having 3 variables, one more slack variable s2 also will be added in the basis, and I have to add these constraints and these rows will remain as it is, as we have seen earlier. So, now in the next one you are having x 2, x 4, x 1 and s 2. So, this is y 2, y 4, y 1 and y 2. CV values are 1, 4, 0, 0, 0. S 1 we have removed already. So, it will be 4, x 4 is 0, x 1 is 1 and s 2 it is 0. So, I am writing it 1, 0, 1, 0, 1, 0. Next one is 7 by 2, 0, 0, half, 0, 0. Next one is 3 by 2, 1, 0, half, 0 and 0. Then S 2 is minus half, 0, 0, minus half, 0 and 1. If you calculate Zj minus Cj, your Zj minus Cj will be 0, 0, half, 4 and 0. So, from here, like earlier case, your Zj minus Cj is greater than equals 0, but one of the basic variable is 2, this is equals to minus half, that is negative. So, it is not satisfying the condition. Therefore, you can use the dual simplex method again on this to deciding what would be the departing vector and what will be the entering vector. If you use dual simplex method, you will find this is the departing vector and this y 3 will be the entering vector. So, that this will be your pivot element. So, from here you make this one as 1 and other 2 as 0 and you will obtain this thing. So, your S 2 this will be your S 2 not y 2. Your S 2 will be going out and S 2 will be replaced by y 3 in the next table. So, in the next table what happens? You are having x 2, x 4, x 1 and x 3 now. So, y 2, y 4, y 1 and y 3. The values are 1, 4, 0, 0 and 0. CV values are 4, 0, 1, 0. So, if you use the row operations to make the element pivot element as 1 and other elements on the corresponding column as 0, you will obtain this thing 3, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1 and 1, 0, 0, 1, 0, minus 2. So, once you are getting, if you calculate Zj minus Cj, you will get this is 1. So, your Zj minus Cj is greater than equals 0 for all j. And if you see the values of the decision variables in the basis is integer. So, therefore, you obtained optimal integer solution. Therefore, your solution is x 1 star equals 1, x 2 star this is equals 1, x 2 is also 1. So, correspondingly z max will be equals to 4 plus 1 that is 5. So, now I hope that it is clear to you that whenever I have to solve one integer linear programming problem and if I find that whenever I am trying to find the solution, in that case in the basis some non-integer solution is coming, then using Gomorian constraint and Gomorian slack variable, I can remove that particular variable from basis, and then since whenever I will use Gomorian slack variable, we have observed that initial value of the Gomorian slack variable will be negative, which is again not satisfying the feasibility condition. So, use dual simplex method to obtain the solution of that one, and by this process you can find out the solution of this. So, this is one of the approach, and there is another approach which is branch and bound method to solve one integer programming problem, which we will discuss in the next class.